Have you ever stopped to wonder how your computer can stream music, juggle dozens of open tabs, and download a huge file all at the same time without even skipping a beat? I mean, it really feels like magic, but it's not. It's the power of threads, the invisible workers that make all of our modern multitasking possible.
To really get our heads around how this works, I want you to picture something. Imagine a busy restaurant on a Saturday night. The place is just packed. Orders are flying into the kitchen, drinks are being delivered, new customers are being seated. It looks like total, controlled chaos, right? But there's a system at play. And that system, believe it or not, is the perfect analogy for one of the most important concepts in all of operating systems.
Okay, so first, think of the entire restaurant as a single process. On your computer, a process is just a running program. Your web browser is one process, your music player is another, and just like that restaurant, each process is its own self-contained environment. It has all the resources it needs to function. The kitchen, the tables, the food, it's its own little world.
And this is where we meet the stars of our show, the waiters. In our analogy, the waiters are the threads. They are the individual workers who operate inside that restaurant. Each one is what we call a single thread of execution, and they're all carrying out tasks independently. You know, taking an order from table 5, delivering drinks to table 9, running a credit card for table 2.
Now, here's the key idea. All of those waiters, all of those threads, are working in a shared space. They're using the same kitchen, the same coffee machine, and they're serving customers at the same set of tables. This sharing, well, that's the superpower of threads. Because they all share the resources of their parent process, they are incredibly, incredibly efficient.
So, with our restaurant analogy fresh in our minds, let's pull back the curtain and dive into the technical details. We're going to compare the old, kind of heavyweight way of doing things, using processes, with the new, lightweight and much, much faster way, using threads.
Okay, so the official textbook definition of a process is a program in execution. But the crucial part of that definition is its own private memory space. Think about it this way. If your web browser process wanted to talk to your word processor process, it's like two completely separate restaurants trying to coordinate. They can't just share a kitchen. They have to send messages back and forth, which is really slow and complicated. This memory isolation is great for safety. It keeps them from messing with each other, but it also makes them heavy and siloed.
A thread, on the other hand, is just one single path of execution within a process. And it's often called a lightweight process for a very good reason. It has just the bare minimum it needs to work independently. Its own program counter to keep track of its task, its own registers for its current calculations, and its own stack for its private notes. But everything else, all the big, heavy resources, they're all shared with the other threads in the same process.
Let's look at this head-to-head because it really makes it clear. Creating a whole new process is slow. It's like building an entire restaurant from scratch. But creating a thread, that's fast. You're just hiring a new waiter. The memory model is the real game changer. Processes are totally isolated, while threads share their address space. And this leads to the final point, context switching. For the operating system to switch from one process to another, it has to save the entire state of that first restaurant and load up a completely new one. But switching between threads in the same process, it just has to save the waiter's notepad and whatever's in their hands. It is dramatically faster.
So the crucial point here, the big idea, is this powerful concept of sharing. It's what allows for this incredible collaboration and efficiency inside a single application. So let's break down exactly what gets shared and what each thread gets to keep for itself.
All right, here's how it works in practice. All the threads within a single process, they all share the same code section. You can think of that as the restaurant's recipe book. They share the data section and the heap, that's the pantry and all the ingredients. And they share open files, like the customer order tickets. But each thread gets its own private stack. Think of this as each waiter's personal notepad for taking an order. And it gets its own registers, which is kind of like what that waiter is physically holding at any given moment. This combination of shared resources and private workspace is really the secret to their success.
And this brings us to a super important distinction, concurrency. See, on a computer with just a single CPU core, you can technically only do one thing at a single instant. Concurrency is the art of making it look like you're doing many things at once. It's like our one hyper-efficient waiter juggling multiple tables. They take an order here, deliver a drink there, run to grab a bill for another table. The operating system is switching between threads so incredibly fast that it creates this perfect illusion that they're all running at the same time.
But with modern computers, we can move beyond just the illusion of concurrency to true parallelism. This is not an illusion.
This is the real deal, executing multiple tasks at the exact same instant. Parallelism is only possible on computers with multiple CPU cores. It's like our restaurant finally got the budget to hire more waiters. Now you can have one thread running on core 1 and another thread running on core 2, both working at the very same time.
Take a look at this. The top timeline shows concurrency. On one CPU, thread A runs for a little bit, then the OS switches to thread B, then it switches back to A, and so on. They're both making progress over time, but you can see they're taking turns. Now look at the bottom timeline for parallelism. With two CPUs, thread A and thread B are running for the entire duration, truly simultaneously. That right there is the power of multi-core processors.
So we've covered the theory, but how do programmers actually command these digital waiters to do their bidding? Let's take a quick glimpse at how threads are actually created and managed in the code. First, it's really important to know that this isn't some obscure optional feature. As this quote from a classic textbook shows, threads are a required fundamental part of the standard for modern systems. And this standardized interface is called P-threads, which stands for POSIX threads.
And actually, using them follows a very logical three-step life cycle. It's pretty simple. First, the main program thread creates a new worker thread. Second, that new thread goes off and starts executing its assigned task, all on its own. And third, the main thread waits for that worker to finish its job before it continues. So, create, execute, join.
It all starts with this command, pthread_create. This one line of code is the instruction to the operating system that basically says, hey, I need a new worker. Go ahead and create a new thread and have it start running this function called myThread. It's literally the moment our new waiter gets hired and handed their first task.
And once that worker is off and running, the main program might need to wait for it to finish its job. And that's exactly what pthread_join does. This call tells the main thread, hey, pause. Don't move on until thread P reports back that its job is complete. This is how we make sure that important tasks are actually finished before, say, we close the entire application.
But, and this is a big but, this wonderful world of shared resources and easy communication, well, it has a dangerous side. When you have multiple threads all working in the same space without some very strict rules of coordination, chaos can erupt.
Let's go back to our restaurant for a second. What happens if waiter A looks at the kitchen's inventory board and sees there's one piece of pie left? They walk away to tell their table. But before they can update the board, waiter B also looks, sees that same single piece of pie and promises it to their table. Now 2 tables have been promised the very last slice. That is a disaster. And in computer science, we call that a race condition.
The reason this happens is because a simple line of code like counter++, which just means add 1 to the counter, it isn't one single unbreakable action to the CPU. It's actually 3 separate tiny steps. First, the CPU loads the current value of the counter from memory. Second, it adds 1 to it. Third, it stores that new value back into memory. The race condition happens when the operating system switches threads in between these tiny steps. One thread can load the value, get paused, and then another thread can load that same old value, creating a critical error.
Now, don't worry. Programmers have developed all sorts of tools like locks and mutexes to prevent these race conditions. And despite these dangers, threads are the absolute non-negotiable engine that powers virtually every single piece of modern software you use every single day. Your web browser? It's using one thread to render the page, another to download images, and a third to respond to your clicks. That's why it stays so responsive. A well-designed app uses a background thread to save a huge file so the main user interface doesn't freeze up on you. Video games, massive web servers, complex scientific analysis, they all rely on dividing their work among many, many threads to get the job done efficiently.
So, the next time you pick up your phone or sit down at your computer, think about that bustling restaurant. Right now, as you're watching this, there are hundreds, maybe even thousands of these lightweight, efficient waiters, these threads, working in parallel inside your device, creating the smooth, powerful, and seamless experience that you just expect. It's a silent symphony of coordination happening every single second.